So what we're talking about today is graphing tangent and cotangent. So we've been talking about sine and cosine, but why are we still limiting? How about we also look at tangent and cotangent? And so the same way we started off section 5.1, I guess while I'm talking about sections, this is 4.3 in the book. 4.3 in the book. So the way we started off 5.1, we're going to start off 5.3 the same way. And we're going to motivate the graphs of tangent and cotangent by just plotting various points. And I have a whole bunch of points here that we're going to reference. So let's go ahead and figure out a few of these values. I might run out of room. Let's see. Okay. That's strange. That is weird. Okay. I don't know what's going on. One second. No, let's try it again. Let's try that again. Weird. Okay, let's try that again. So I'll do it over here. So some of the x values we'll plug in, and I'm going to use the calculator solely for all of this. We're just going to get decimals. And that's okay because we're just simply plotting the graph. So it's okay if we get a bunch of decimals. All we're trying to do is plot stuff on the graph. So we don't need exact answers for this initial setup. So if we have, say, negative pi over 2, negative pi over 3, pi over 4. Let's try some of these out and see what happens. Really, I should have done it like this. I changed my mind again. I changed my mind one more time. Negative pi over 2. And we're going to keep plugging in these values really into the calculator, which means you need to make sure your calculator is in radian mode for this to work. So when I type in tangent of negative pi, I get 0. Anything? All right. Put a 0 right here. We'll slowly start to derive what this graph looks like. About tangent of negative pi over 2. It says I get a domain error. So that normally means undefined. So what that means, well, it's normally a divide by 0 issue. We're going to have an asymptote here. We didn't have this with sine or cosine, so this is kind of an interesting situation. Let's keep going and see what more is going to happen. Negative pi over 3. Negative 1.73. Remember, your calculator needs to be in radian mode for this to work. If it's in degree mode, you're probably, for this value, you would get like a really, really small number. But negative pi over 3, I get negative 1.73, so that's probably about right here. Maybe not that far down. It doesn't have to be perfect. About right there. And if we keep going, What about negative pi over 4? Or negative pi over 6? What do these values give us? This one's a pretty nice number. We just get negative 1. So we can plot that one pretty easily. Then what about negative pi over 6? Negative 0.577. That's about halfway here. So we could plug in 0 and pi over 6. Pi over 4, I'll just write out the rest of them. Pi over 3, pi over 2, and pi. So what happens when we start plugging in all of these values? What do we get? 0 for 0. Okay. Go right at the origin. Pi over 6. Oh, that's a familiar number. 0.557. Okay, so that'll be probably right here in the middle. Pi over 4, we get 1. Pi over 3, 1.73, so that'll be closer to 2, but not quite a 2. And then pi over 2 gives undefined. And pi gives us 0. Okay, so this is pretty interesting. So, pretty interesting here. So we have all these dots seemingly scattered in some arbitrary manner. Well, tangent is closely related to sine and cosine. In fact, tangent is simply the ratio of sine and cosine. So the arc-like structure will be retained. So in blue, well, one thing to notice, and this comes back to algebra, whenever you have these asymptotes, as they're called, asymptotes, graphs generally will converge to the asymptote. If there's an asymptote, a part of your graph will be tracing it ever so closely, never touching it, but getting closer and closer and closer forever and ever. So coming from that direction, slowly have this arc-like structure. Now really, this is not a good shape. I tried practicing this one and every time it just looked bad. A true sense of what this graph should look like. You can figure that out fairly quickly. More like an x to the third kind of shape. So really this is, really this is the shape that I failed to draw. But you can see examples pretty quickly. It's kind of like an x to the third type shape almost. Except it levels off at those vertical asymptotes. So that's the shape I'm trying to convey and doing a poor job of illustrating. It looks even worse looking at it now. So this should be more so of an arc, but I digress. And they do go up and down infinitely. And really, if we were to continue this, because this does continue onwards, really the shape of it, well, that's not too symmetric actually. Really the shape should look like this. And the next asymptote would be at, well, 3 pi over 2. And then the same thing over here. I'm just not very good at drawing these, to be honest. Which means I won't expect you to be good at drawing these either. But you get the idea. It does something like that. So it just repeats like that. Just pieces of that just get copied again and again and again. So that is the graph of tangent. And so example 2 immediately asks us a question that we asked about sine and cosine. What is the period of tangent of x? What is the period? It's a good question.
It's pi, right?
Why is it pi?
Because from negative pi over 2 is pi.
It is pi. So remember, the period represents what is the width of the repetition. So what is the width of that repetition? And we see that all the repetitions happen between the vertical asymptotes. Because once we copy that over, we get the same exact shape. That is the repetition. So what is the shape of this? As Blake pointed out, starts, well, one situation starts at negative pi over 2 and ends at pi over 2. The difference between those is just pi. So we no longer deal with a period of 2 pi, like we did for sine and cosine. The period of tangent is just pi. So when we work problems like this, instead of it being 2 pi divided by the number, it's going to be pi divided by the number. That will be our default when we deal with tangent problems. That is the graph of tangent, and that's the period of tangent. Also, the number of pieces, I might as well. So it says how many pieces should we use? So this is kind of this is kind of my preference as a teacher. There's no set in stone number. I'm going to ask for, well, when I say pieces, I'm going to multiply it by 1/2 instead of 1/4. So that means instead of 4 increments, we're going to have 2. So that means you will only have to list 3 interval values instead of 5. So just to clarify what that means. So that it's multiplying by 1/2 and then 3 interval values instead of 5. So we're not breaking it up into fourths, we're breaking it up into halves. And this will be clear later on. We're also going to go ahead and use the above information to go ahead and sketch cosine, or not cosine, cotangent. And remember, cotangent is just tangent flipped. So we're going to keep all of those above values in view as we go through cotangent of x. So it's going to be the same values though, negative pi over 2, we'll keep going. Okay, so we don't really need the calculator for this because all we have to do is take the above corresponding values and flip them. Well, I want to figure out negative pi, for example. For negative pi, we take 0 and we reciprocate it. So instead of 0 divided by 1, it's 1 divided by 0. That's undefined. So that means here, we're going to get an asymptote at negative pi. Here's kind of the tricky part as well. What about the next one? Negative pi over 2. How do we reciprocate undefined? It is going to be 0. Because undefined, in this context, represents 1 divided by 0. What happens if you reciprocate 1 divided by 0? You get 0 divided by 1, which is 0. So that one's a little bit of a tricky one. If you put that in your calculator, it would tell you undefined. So that's why we have to be smarter than the calculator this time. And then really, we just keep taking values and look at them divided by 1. But really what I'm going to do is 1 divided by tangent of negative pi over 3. Or you could just reciprocate negative 1.73. It really doesn't matter. We're just trying to get approximations. So I guess I'll do that. I'll just reciprocate all the values. So it'll give us a pretty close approximation. So this right here, in the calculator, I'm literally doing 1 divided by negative 1.73. And I get negative 0.578. Maybe I should have given myself some more room here. Negative pi over 4, I'll just take the next one. Well, negative 1. It's just 1 over negative 1, which is still negative 1. What you'll end up noticing is you'll alternate kind of between the 1.73 and the 0.577 value. That is not a coincidence. I just won't get into it right now. Oops. Let's go ahead and start plotting these. I'll put 0 down as well, which is undefined. So when you try to reciprocate 0, you just get 1 over 0, which is undefined. So you would end up getting another asymptote on the y-axis this time. So let's go ahead and start plotting some of these. At negative pi over 2, we got 0. Negative pi over 3, we got negative 0.7 or 578. We get negative 1, negative 1.73, like that. Okay, so we only have what seems to be half of that little region. So let's keep going. Let's see what's on the other side. See if that helps us out at all. Pi over 6. You can reciprocate 0.577 to get 1.73. That'd be right up here. Pi over 4. Reciprocate 1 to get 1. Pi over 3, pi over 2, and pi. We can reciprocate 1.73 to get 0.578. We've got right here, pi over 2 is going to give us 0, and then pi is going to give us undefined. So this is what we get once we plot everything. So what we end up observing here, what we are observing here is really the points that we found, they're centered towards the y-axis. They do complement each other pretty well, and to the extent that these points can be generalized via understanding of the repetition. So really what's going on here, if we use this side, if we connect those dots as such, knowing that the graph's going to trace the asymptote, then really the dots on the other side paint a picture as to what to expect over here as well. So really the dots are going to go in the same kind of manner. And this has to do with certain reflective properties of tangent as well. Certain cyclic properties more so. And we can also paint the same picture over here. Okay, so those aren't as bad. They're still kind of bad, but that's okay. So really, this is the repetition now. So it's still this repetitive thing. Notice that as we compare these two graphs, one of them increases and one of them decreases. So as we try to fit both of these in to the screen, so as we can see, one of the graphs increases, the tangent one, as opposed to the cotangent graph on the bottom, which decreases naturally. Additionally, notice that the asymptotes are in different places. For the tangent graph, the asymptotes are at negative pi over 2 and pi over 2. They are not on the y-axis. As opposed to example 3, which shows cotangent, where the asymptote is on the y-axis and is at pi. So the generalization here is that tangent has asymptotes on all the multiples of 1/2. And it goes in increments of pi, because that is the period. As opposed to cotangent, where the asymptotes lie on intervals of pi with a period of pi. That goes right into the next question. What is the period of cotangent? Well, the period of cotangent is pi. Because the width between the asymptotes, where the repeated information is happening at, is pi. Then how many pieces? It's going to be the same as before. You're just going to multiply by 1/2, and it's the same thing as before, 3 intervals instead of 5. It's a bit crazy because you don't have to derive any of that on your own, but it's a good way to kill 30 minutes. That was kind of fun. But it does help us understand some of the processes that we will be doing momentarily to sketch these various trig functions. So I put a note here. The range of tangent and cotangent is all real numbers. The range is all real numbers, so there's no amplitude. It doesn't make sense to define an amplitude because what did amplitude represent? Well, it helped us construct peaks and valleys. How can we have a peak and a valley for something that continues upwards forever and downwards forever? Doesn't make any sense in this context. So really, because of that, I will make sure that any of the numbers multiplying the function itself stay between 1 and -1. I'll just make things a little bit easier, because that gets a little bit fishy in this case. So there's no amplitude to worry about. So now let's see how all of this will correspond for, I don't know, let's look at a standard tangent problem. And really, you're going to see a lot of the stuff from the previous section recycled. We will have to change up some information, though, naturally. One of the things, well, there's no amplitude, so I don't have to put anything for the amplitude. If you want, you could just say, if it makes you feel better about having all the steps in order, you could just say amplitude none. If you don't want to put it, you don't have to put it. That's fine. But if it helps you with, having a repetitious process, if it's consistent with the other sections, you could put it. It doesn't matter. I'll keep it there for no reason. The period is still affected by the same number. It's the number that multiplies the x. So 2. 2 is going to be the number that affects the period. But here's the kicker. We're not using 2 pi divided by 2 anymore. It's going to be pi divided by 2, right? Because period is now, the original period is now pi. So notice that's no longer 2 pi. That is on purpose. It's because that's what happens when we deal with tangent and cotangent. So really, there's nothing to do there. So that is the period. We do not have 2 pi here anymore for tangent and cotangent. Now the pieces. You still drop whatever the period is down, but we're not multiplying by 1/4 anymore. We're multiplying by 1/2. And also, I forgot to put that there's no vertical shift. Didn't I normally put that after the amplitude? So, actually, just to stay consistent. Vertical shift, there is none. Just to keep everything in order, because we're not adding anything to the function as a whole. So let me go back to the period, which was pi divided by 2, and the pieces, pi divided by 2 times 1/2, which is pi/4. And now we can, before we state the interval, we talk about the horizontal shift. Logan, you want to take a crack at the horizontal shift? If not, that's fine.
To the right pi? Or no, to the right pi over 2?
Yeah, to the right pi over 2. Remember, there's still that wonky detail. So we have to rewrite this, as you may recall from your homework, where you factor out the 2. So this gives us the true horizontal translation. Remember, this is the opposite of distribution. So this is, when you distribute, you multiply. So if it's the opposite of that, you divide. So really, the horizontal shift is to the right, pi over 2. Because now this gives us the true picture of what the horizontal shift is. It shows us what's actually subtracting from the x value directly. Before we did not have, so pi was not subtracting the x directly. So now, all right, so this is where things are going to get slightly different. Stating the interval values, and I guess I'll also say there's a reflection. Go ahead and just put that. Same as before, there's a reflection because there's a negative sign in the front. The interval values, okay, this is where it gets weird. Because tangent, so let's go, I'll go back down in a second. Because tangent starts at 0, it has a point at the origin, that means the asymptotes will be to the left of that starting value and to the right of that starting value. As such, so remember I said we only need 3 interval values. So the good news is that there's less of them. The bad news is there's a trick just reserved for tangent. Cotangent doesn't use this one, but tangent does. So pi over 2 is where we start, but we have to find a value to the left of pi over 2 and to the right of pi over 2, instead of going all to the right. It's because the values we find to the left and to the right will be the asymptotes. So pi over 2, I'm going to do this off to the side. So we have to go to the left and to the right of that center point. And the center point is always characterized by the horizontal shift. So what is the increment? What is the counter? How much do we go? So we have to subtract pi over 4 to go this way and add pi over 4 to go this way, because that's the piece size. That's the size of the pieces. The horizontal shift tells us where to start, and the pieces tell us how much to move. So then you should get pi over 4 and 3 pi over 4. And that's your interval values. And so by doing it this way, it will always be true for tangent, or even for tangent as well, that your first one, your first interval value will have an asymptote, and your last one will have an asymptote. That will always be true. And because there's not a vertical shift, pi over 2 is going to have the x-axis. Well, we're going to shade in the at the x-axis. We are also reflecting about the x-axis. which means instead of increasing, we're decreasing. But the good news is we don't need any other points of reference. All you have to show me see, why can I draw that one so much better? That was so easy. Okay, whatever. See, that's all you have to do. It doesn't have to be perfect, but see, there's no other points of reference. That is all I need to see, because anything else that goes on in this graph will just be a direct copy of this. So there's no need to add it. This is a 1 period interval. And so please, when you do the homework, even if it's clear to you what the steps are to take, just write out all the steps as I have them here. So pieces, just write that down for me. Just add that intermediate step. If there was more to do for the period, I guess you would write down more stuff for that, but it does help me to make sure that you didn't just snag this from the back of the book or online. I won't be a stickler about it now, but on the Unit 3 test, or whatever I called it, I will be a little picky about it.
So we need to write on the pi over 2 times 1/2. So that we can't just put like pi over 4.
Play it safe. It's my way of making sure there's not too much to show your work with. And again, I need something, especially if it's a test that I'm not able to proctor. So this is my way of making sure that you are constructing the graph in the right way and not having your calculator construct the graph in the right way. Because I know the calculator can do it. Probably do it really well. All right, so that's the process for tangent. Yes?
Is it 2 period interval whenever there's going to be multiple of those?
Is the 2 period interval, say that again?
Like if for our homework it asked for a 2 period interval and I got caught up on that last time.
Just do 1 period, that's fine. If it says
Okay.
2 period, yeah, that's a good question. I forgot to clarify that. If it says 2 period interval, just ignore that. 1 period interval is fine by me.
Okay.
2 period, you would just end up drawing the same thing again. I'm okay with this.
Yeah, you just basically find more intervals, right?
Yeah, unless you want to find more intervals. Doesn't that sound exciting? No, it doesn't. Sounds like more apt to grade. So, no, I'm okay. So, yeah, the starts with that. What's that?
Yeah, but it's 2 period for that.
I did
It's
2 periods.
not
You're like, okay, I'm gonna stop.
It's not
It's the
anything.
second period.
it's not anything more apt to grade. I was just kidding. It's nothing crazy. All right. So does anyone have any questions before we move on to the cotangent one? Let's do the cotangent. I think you can tell which direction we're going to be shifting, hopefully, by this graph. I think it's a little clear. Okay, so start off. If you want, you could put the amplitude as none. If you just enjoy having the list that's unchanged for all the trig functions. Vertical shift. Well, if you want to, you can go ahead and rewrite it now, even if it's not really much of a change. I saw some people do this in the homework, and that's perfectly fine. You know, if that helps you see the problem better, that's fine. But here it's clear the vertical shift is down 2. Now there's no immediate translation of this to the graph like we did with the amplitude, so we're going to hang tight with that information. We are going to apply it. And so, the period. So for tangent and cotangent, the period is normally pi, but then we have to divide by whatever's multiplying the x. So that's 2. It's just the 2 is factored out for us already. If you distributed the 2 back in, then you would see. So the pieces, well, this is going to be the same as before because we have the same period. And we're still multiplying by 1/2 to get displacement, a displacement of pi over 4. And the horizontal shift to the left pi. So if anything, that gives us the starting point. And we don't have a reflection, so cool. So for the intervals, we are going to just start at whatever the horizontal shift is. We don't have to go left or right. And the reason why it's different here is because for cotangent, the point you start off at is an asymptote. So wherever you shift that, that's where you're shifting the asymptote. So that's why we're going to keep the first point. We're going to find the next 2 points. Remember, that's we're going to be adding pi over 4, because that's the piece value. So negative pi plus pi over 4, negative 3 pi over 4, and then negative pi over 2. Now the nitpick side of me is going to plot these interval values in a specific way. I'm going to plot them like this. You might not even notice what I did. I skipped the first tick marker over here.
Because that's pi over 4.
Yeah, that's negative pi over 4. You could put the negative pi over 2 over there, and I would probably think in my mind, oh, that's kind of gross, but I don't care that much. But yeah, these go by increments of pi over 4. But the reason why I want to have some consistency here between the tangent and cotangent. So tangent and cotangent is always going to have asymptotes. That's just how they work. So in both, the way I have you all do this, the first value you always list will always have an asymptote, whether it's tan or cotangent. And the last one will always have an asymptote. It's just how do you find those interval values is what is distinguished between these two. Additionally, so normally what we would do, I'm going to do this in red because I'm going to erase this. We would put the point in the center and start to draw the graph. But we have a vertical shift. We're shifting down 2. So that point, guess where that point goes? All the way down here at -2. And now we can draw the graph. like how I unintentionally dodged the scratch work with my graph. I don't know. I thought that was kind of cool.
And,
When you're a mathematician, cool stuff doesn't come up that much.
well,
You got to make the best of the little things.
it's weird, like, so when you flip, tangent over the x-axis, it almost becomes cotangent in a way.
I mean, it's the same shape. It's just, well, remember, tangent and
It's a different-
cotangent are cofunctions,
Yeah.
which means if you shift one of them 90 degrees, they will virtually line up. But there is also this they're also reciprocal identities. So that's why there's this duality between the two, given these two different characteristics for which they are associated with each other. And that association, the fact that they are the same shape, just flipped, is really the causality behind their dual association with one another. It's really kind of interesting to see it, scale so consistently to some sort of visualization. Especially in rectangular coordinates, which you'll learn about other coordinate systems at the end of this class. Wouldn't imagine anyone here is taking Calc 3 anytime soon. They talk about coordinate systems in there. We'll talk about polar coordinates, I think, from the last sections. But in any case, does anyone have any questions about this? Because depending on how quickly I get done with the next section, I was just gonna work out a homework problem or two from the upcoming one, because I feel like this isn't enough examples. So let's see how quickly I get through 5.4. But the homework for this section is gonna be due Tuesday. The homework questions being, well, those. So remember, this is 4.3 in the book. And depending on how much time I have, I might work out one or two of these. So again, that's due Tuesday. Cool. All right, scroll down a little bit. So the good news is this killer homework assignment, which is none. There's no homework for it.
I don't think we can handle that.
Well, too bad. Here, I'll double the homework assignment then.
0? Yes.
That's right. You have twice as many homework problems now. It's weird that I'm right as well. So really, this is of course, the natural conclusion to graphing the various trig functions, and it's graphing secant and cosecant, the last two that we haven't touched. So really, it just is a matter of, well, figuring out what sine does and then applying that to cosecant. And again, we can use various decimal values to figure this out. So what I'm going to do X here, it says use sine, and then we can construct cosecant. And we'll use all the special angles that we've been dealing with, -2 pi, -3 pi over 2, -pi, -pi over 2, 0, and keep going. Cool. So wonder how good everyone's memory of the various sine values are for some of the special ones. And maybe, well, yeah, these are all quadrantals. So that means 0, 0, 0. That's just for sine, not cosecant yet. So pi over 2 is 1, 0, negative 1, 0. Then negative 1, 0, 1, 0. So these are just quadrantals. I didn't even throw the special, the 30 degree, 45 degree, 60 degree ones. Because really this section is not too important, I guess. So really, how does this translate to cosecant? They're just reciprocals. So all the 0 ones are going to be undefined. Okay, so there's a reciprocal. Let me use red. So that one's an asymptote, that one's going to be an asymptote, all the ones where it says undefined. And then there's some various other points that we can plot. So there's 1, it's negative 1, 1, negative 1. Cool. So really that tells us nothing, really. I mean, it tells us a little bit, but nothing crazy. What about if we also considered, because all these, I'm kind of jumping the gun here, all the reciprocals of these are obviously going to be themselves. You flip 1, you get 1. You flip negative 1, you get negative 1, and so on. So really, let's go ahead and look at 3 more. Let's look at the special ones. Pi over 6, pi over 4, pi over 3. Let's look at the special ones. So that would be here, here, and here, in order. Sine, then we'll look at cosecant. Who remembers pi over 6? Sine of pi over 6. Okay, it's 1/2. In fact, we're just going to use decimals. That's okay. 0.707 and 0.866. That's what you'll get for all of them. So naturally, we're just going to reciprocate all of those and see what happens. Obviously, 1 divided by 0.5 is just 2. 1 divided by 1 divided by 2, 2. 1 divided by 0.707, 1.414. 1 divided by 0.866 is 1.155, I guess. Doesn't have to be perfect. But what this tells us in order is that the points are slowly decreasing to 1. And because of other reasons I don't really want to get into because they're not important, I'm just going to go ahead and use this to graph function. It turns out because sine is positive in quadrant 2, then these values will be symmetric over here as well. Again, you don't have to know that, but pi over 2 is where quadrant 1 and 2 differ, and sine is positive in quadrant 2, so naturally that displacement along with the continuity of sine would guarantee the symmetry at pi over 2 from the domain of 0 to pi. So if anything, it also does the same thing over here. I guess the question remains, what about those other two dots that are just at -1?
Well, they're negative there, so wouldn't they just go down?
Yeah, you think, well, does the cup go up or down? And for reasons I don't feel like getting into, mainly due to quadrant stuff. I don't know how I feel about what you just said. Calling those parabolas. That is so not a parabola, but
Wait,
that's the nitpick in me. I know it does look a lot like a parabola.
it looks like it.
It looks like a parabola.
But you know, once you.
If it, what's the saying? If it talks like a duck or something, quacks like a duck, looks like a duck, and it's a parabola. Yeah, I forgot about that saying. All right, so really nothing I want you all to focus on too much about this, other than, well, the last extension that we are going to take from this is, what's the period? What's that?
It's pi.
No. So what you're saying, so for example, so this would be 0 to pi, you would say that this and only that repeats. It's 2 pi. You need to go a little bit further. So it's 2 pi, because the upper and the lower part together is what repeats again and again and again. So pi for the upper part, pi
If
for
it were
the,
just pi, it'd just be upper.
yeah, if it were just pi, it would just be up, 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 up the whole time. So it's 2 pi. And that makes sense because so cosecant is just the reciprocal of sine, and its period was 2 pi. So kind of, you know, kind of recycled stuff. Pieces, doesn't matter. We're not doing anything with pieces. We're not doing anything with this. It doesn't matter how many pieces. If anything, we would use 5, or, you know, we would do the same thing as we did with sine, but
So 4 pieces, 5 intervals.
yeah, 4 pieces, 5 intervals, but I mean, we're not doing anything with this. Really, it's, as the homework says, just know these graphs. If I asked you a test question on it, it would be something very, you know, basic. Could be, what's the period of random trig function, or what's cosecant at doing at pi or something. It'd be something very simple like that. Wouldn't be anything crazy. And so we can do the same thing for secant, which is just the reciprocal of cosine. So if we started off with cosine and then made our way to secant, we can use the same values, -2 pi, -3 pi over 2. So these are the quadrantals, of course. -pi, -pi over 2, 0, pi over 2, oops, got pi. Pi over 2 pi. So when it's cosine 0, 0, 0, 0, all the over 2 ones. That's when cosine 0. 1, -1, 1, -1, 1. And so naturally, 1, -1, undefined. So there's still a bunch of asymptotes. They're just going to be shifted. So it's this W looking shape. And without really spending too much time talking about why it is the following shape, I'm just going to draw it. And this makes sense because in terms of the comparisons between secant and cosecant, because secant and cosecant are co-functions, which means if you take one of them, shift it pi over 2 radians in either direction, really it's to the right, then they would overlap each other. So really they're very similar, and they are so similar in fact that we can assert that they have the same period. It's 2 pi again. They're the same exact logic as before. Again, pieces, I mean, it'd be the same as before. You want to put that there'd be 4 pieces, 5 intervals. Feel free, doesn't matter. I'm not going to ask you for it. So from here, since we have about 9 minutes left, I figured I'd do 1 or 2 of the homework problems for this newest homework I'm asking for. Why not? Hopefully everyone's written all that stuff down by now. This is 4.3 in the book. Let's see, we'll do a nice tangent 1 and a cotangent 1. See, 14 and 19 look a little easy. 20 is a little interesting. 25 is pretty cool. 26 also looks interesting. Huh, what 2 should I do? Who's got their book out? Anyone? Nope. All right, let's try that again. 28 looks pretty hardcore. 32. If anything, I'll do 28. So you're saying 26 and 32. All right, strike a deal. 26 and 28. Cool. So open up one of these. Go to 26 and 28. It's a nice tangent 1. It's a nice cotangent. Twenty-six. Y, and it says 2 period interval. Again, ignore that. Just do 1 period. That's fine. I don't care. I guess while I'm at it, go ahead and put 28 down here. Cool. So Blake, what's the amplitude?
There is none.
There is none. It's your question. All right, want to redeem yourself? It's a vertical shift.
There is none.
Exactly, there isn't one. Another trick question. All right. Might be a little bit more difficult. It's a period.
Two pi,
It is 2 pi.
because you have to multiply
So
two and
if anything, hopefully everyone remembers we got to start with pi, not 2 pi, for the basis. So really it might help. So we're going to divide by something. I'm going to rewrite it this way. Wait, what am I doing? I'm sorry. That should be x. And then in that regard. This is the same exact problem. They did that on purpose. They 100% did that on purpose. And then I guess while we're at it, so what is that one going to be?
two pi.
That is 2 pi. That one's tricky. That one's definitely tricky. Because you're dividing a fraction. You're dividing by a fraction,
Or multiplying, basically.
or you're multiplying by the denominator. So really, so the period, and we'll see this exactly here. So what's the number being multiplied to the x? It's 1/2. So we're dividing by 1/2. Which is equal to multiplying by the denominator flipped, which is just 2 pi. And it's the same, it's that same logic why there's a 2 pi right here in blue. Same exact logic. Because we factored out, and that's just a coincidence, but we factored out a 1/2, which meant we divided pi by 1/2. Or if it makes you feel any better in your calculator, you can do 1 divided by 0.5. You're not good with fractions. Now we'll get to how many times does a half go into 1? Yeah, how many times does a half go into 1? Twice. You want to think about it from a fundamental level. All right, so that's the period, pieces. Bring down whatever the period is. And you multiply that by, we're doing 1/2 now, not 1/4 anymore. So that's pretty nice, it's just pi. But what about the horizontal shift? Definitely going to the left. Yeah, 2 pi. Because the reason why we rewrote it here on the far right was to figure out the true horizontal translation. So how did we figure out these intervals again?
It's tangent, so you start with the horizontal shift being in the middle.
So 2 pi,
And the second one.
2 pi. Why no? Why not 2 pi? It's negative 2 pi because it's to the left.
One on the right.
Yeah, we need to figure out one on the right, one on the left. So the increments are by pi because that's the piece value. So we're subtracting pi, we're adding pi. So negative 2 minus 1 in essence is negative 3 pi. And then just negative pi. And there's no reflection, so we can go ahead and start graphing this. So let's see. I'm going to keep them all to the left of the y-axis because they are negative numbers. You want this to be a little bit, want this to make a little bit of sense. Always the first value you list and the last value you list will have asymptotes. Since there's no vertical shift, we have this point right here on the x-axis in the middle. And tangent, since there's no reflection, is an increasing function. So, that's a really good graph. That's a really good graph. I'm proud of that. What you got?
So we only need to write down reflection if there is a reflection in the problem. Otherwise, I don't have to write it on the homework. I don't have to put none down.
Nah, not really. Since I'm out of time, I just want to give a hint for number 28. What number goes next?
It's gonna be 5.2 again.
So what number goes in that little blank I have left there? Yep, it's 316. People are getting mad.
So you would basically, that'd be doing it by, if like multiplying it by pi over 2, right?
That's it. You're dividing by 2 to something that already has 2 in the denominator.
So you just multiply the denominators.
Ultimately, yeah. And if you distribute back 2 and the 4 would simplify to 1 over 2, then you just get 3 pi over 2. So that form right there should help you with a lot. So that's my hint for that problem. I'm definitely over time, so I will stop it there. If you have any help if you need any help with this homework, just shoot me an email or something. I like trig. You're not my college algebra, so I like helping.
So if we wanted to help with college, honestly, you wouldn't help.
That's a paradoxical in a sense. I'll think about it. Every situation's unique.